Welcome to this explainer. Today, we're setting the stage for a truly epic 4.568 billion year journey. Just to put that massive scale into perspective for a second, if a whole century passed by every single second, it would still take you over a year of non-stop watching to witness the birth, the evolution, and the ultimate fate of our cosmic neighborhood.
Here is our roadmap for today. We're going to cover 1. Birth of the solar system, 2. Planetary migration and chaos, 3. The clockwork orbits, 4. The terrestrial neighbors, and finally 5. The distant future.
All right, let's jump right into Section 1, Birth of the Solar System. Rewinding the clock back to year 0, the whole process kicked off when a giant pre-solar nebula collapsed. Thanks to the conservation of angular momentum, kind of like an ice skater pulling their arms in so they can spin faster, this massive cloud began rotating faster and faster. This caused it to flatten out into a sprawling protoplanetary disk about 200 astronomical units wide. Over 99% of all that mass fell right to the center, while the leftover dust began the agonizingly slow process of planetary accretion. But notice how incredibly rapid this cosmic birth was on a galactic scale. Within just 50 million years, the pressure and density of hydrogen at the core became so insanely high that thermal nuclear fusion actually ignited. And that brilliant ignition brings us to hydrostatic equilibrium. This right here is the exact moment our sun was truly born as a main sequence star. It's essentially the ultimate cosmic tug-of-war. The explosive thermal pressure pushing outward from nuclear fusion perfectly matches the inward crushing force of gravity. The sun had finally found its balance. Moving right along to Section 2, planetary migration and chaos. So while the sun found its balance, the rest of the neighborhood was definitely not calm. After the protoplanetary disk dissipated, the early gas giants had these extremely close gravitational encounters with smaller, rocky bodies, known as planetesimals. According to the NICE model of dynamical instability, these encounters acted like a giant cosmic slingshot. They caused the gas giants themselves to migrate into entirely different orbits through compounding gravitational perturbations, which violently scattered literally everything else in their path. The crucial takeaway here is that early Jupiter acted like an absolute wrecking ball. The grand tack hypothesis suggests Jupiter actually migrated inward toward the sun and then reversed course. Think of a sailboat catching the wind and tacking back. It plowed right through and dispersed much of the early asteroid belt. And this triggered a massive bombardment of icy and rocky debris that heavily impacted the interterrestrial planets. We fittingly call this era the Late Heavy Bombardment. Let's fast forward to Section 3, the clockwork orbits. To really understand the stable equilibrium we see today, we have to look at Kepler's laws of planetary motion. Rather than traveling in perfect circles, objects travel in an ellipse. This means a planet's distance from the sun actually varies over the course of its year. It speeds up at perihelion, its closest approach, as gravitational potential energy converts to kinetic energy, and then it slows back down at aphelion, its most distant point. It's a beautifully complex, highly predictable dance. But we have to remember, the space between these orbiting planets isn't just an empty vacuum. The sun is continuously blasting a stream of charged plasma outward, the solar wind. And wow, is it moving fast? At its peak, this solar wind rips through the space between the planets at a blistering maximum speed of 2,880,000 kilometers per hour. To put that into perspective, at that speed, you could zip from the Earth to the Moon in under 10 minutes. This high-speed solar wind pushes relentlessly outward against interstellar space to create what we call the heliosphere. You can think of it as a massive protective atmospheric bubble dominated by the sun's magnetic field, extending well past 100 astronomical units. That bubble defines the true physical boundary of our solar system. And honestly, without this invisible protective shield pushing back against harsh interstellar radiation, life on Earth as we know it would likely be impossible. Which brings us nicely to Section 4, the terrestrial neighbors. Now that we've mapped out the grand mechanics, let's zoom in on our own terrestrial sphere. When we compare Earth's moon to Mars, we see starkly different evolutionary pathways. The moon is about 1/4 Earth's size. It lacks sufficient gravity to hold gases, leaving it a heavily cratered, dead vacuum marked by dark volcanic maria. Mars, meanwhile, is larger. It clings to a thin carbon dioxide atmosphere that is just dense enough, sitting at about 0.6% of Earth's pressure, to actually support real weather phenomena. Looking closely at Mars, the geological diversity is fascinating. We're talking red iron oxide soil, polar ice caps made of water and CO2, massive surface temperature swings, and deep rift valleys. But you know what the most critical feature is? It's what's missing. Around 4 billion years ago, Mars' internal core cooled down, completely shutting off its internal magnetic dynamo. Without a magnetosphere, the planet was left totally defenseless against that high-speed solar wind we just talked about, which slowly, methodically stripped away its early atmosphere.
Finally, let's look ahead to Section 5, the distant future. It's kind of a jarring thought, right? Especially when everything seems so reliable to us today. The sun rises, the planets orbit exactly as predicted. But it forces us to ask the big question. Is this perfect clockwork equilibrium permanent? Well, on a human timescale, numerical models assure us that everything is perfectly stable. Don't worry, we aren't going to randomly crash into Venus tomorrow. But over billions of years, tiny gravitational perturbations between the planets compound. This means that, mathematically speaking, our solar system is secretly chaotic, and long-term orbital destabilization is an inevitable feature of the system.
And the very anchor of our system, our sun, is also ticking towards its own demise. Because nuclear fusion continuously converts hydrogen into helium, that helium is steadily building up in the core. As a result, the sun is actually burning brighter and brighter over time. Fun fact, early in its main sequence life, it was only 70% as bright as it is today. As it gets hotter and exhausts its fuel, it's charting a definitive, irreversible course toward becoming a giant red star. As its outer layers expand, it will engulf Mercury, Venus, and very likely Earth itself, before eventually cooling into a white dwarf. I want to leave you with this final provocative thought. It reminds us that in the grand, sweeping timeline of the universe, our deeply familiar cosmic neighborhood, the steady orbits, the protective heliosphere, the warm sun, is really just a beautiful, temporary arrangement. Thanks so much for joining me for this explainer, and keep looking up.